A tutorial here on working with concrete formwork design, in this case a slab, um, overhead slab supported by shoring and formwork. So basically we can see the situation that we're designing for here kind of in this graphic here, and to look at a different way of solving these problems, maybe a more eloquent way to, if you're going to be doing this more often or need to make iterations, we're going to look at this in Excel real quick. You have an example on the website of doing this by hand, step by step, but we're just going to look at a problem here. So you have this situation over here. You're looking at these for your given design criteria. So you have an 8-inch slab. Your initial design right now is 1-inch ply form class 1 sheeting. You're going to be using 2x10 joists, 4x8 stringers. Your shores that you have available are rated at 6,000 pounds. The max deflection is going to be L over 360. Concrete unit weight that you're going to use is 150 pounds per cubic foot. Formwork weight, we're going to use 5. You can find that. Some of this, like the ply form, has a self weight. You can find weights of these members in your in different design manuals. We don't have it in the references that we're going to be pulling from, so we're just going to provide that as 5 right now, and then we're going to assume 3 or more spans. That'll come in handy. So the first thing to do when setting this up, and even if you were doing this on paper, would be really handy, is to make this table right here. This is basically going to be everything you need as far as the design criteria. So you've got dimensions, you've got all of these characteristics and capacities for your different things. So first things first, you look at our sheeting, and we get this from your tables. A lot of this information is coming from right here. So we're looking at the 1-inch sheeting. Here's face grain across the supports is what we're going to assume. EI, FBKS, FS, LB over Q. So you use that, punch all those in. It's good to keep track of your units, and there's that. Then the problem is going to state, in this case, we're going to assume southern pine. So southern pine characteristics for all of these values, we're going to look again here, but we're going to look at the table here for southern pine. And here's all of these allowable unit stresses in PSI up here. Okay, so we've got that all squared away. The next thing is we're going to take here, and you can see here that I ended up using the actual dimensions right here, just because I'm going to refer to that a lot in the equations. And then over here we're using the actual. So the nominal I just kind of have in parentheses here to keep track of, but when we're doing all our calculations, we want to use the actual. So as we start here, this data for 2x10s and 4x8s all come from this chart, table 8. So here's your 2x10 information, and your 4x8 information is all down here. Okay, so now that we've got that all organized and squared away, we made sure we kept our units. We're going to start looking at this design. So starting with the design load, we're going to start with the weight of the concrete. So the weight of the concrete, and you'll see my equation plugged in here, is going to be the concrete unit weight times the slab thickness over 12, to put that in feet, and times a 1-foot strip, because that's what we're going to analyze, is a 1-foot strip thickness here. So that gives us 100 is our pounds per square foot of concrete. Our formwork was given as 5, so that just refers to there. and our live load, our live load is 50. 50 is the ACI recommended live load for this application. So you just sum that all up, and you get your total, or capital W. I'll even put that in there so we can refer to it as capital W. Okay, so that's step one. Step two is going to be our deck design or joist spacing. So what we're going to do, as we talked about before, we're looking at a 1 foot strip of decking here. So we take our capital W times the spacing of 1 foot, comes out to 155, of course. And now we're going to look at the 3 different failure criteria for the spacing of our joists. So this is basically telling us what span these joists can, or what span the sheathing can handle, and that means how far apart we can place our joists, if that makes sense. Basically, you have your sheathing here, and that's what we're analyzing, is actually the sheathing, to see how far apart or what size span this can handle before it fails. And that means we have to put our joists at that distance or shorter in order to get a proper design that's not going to fail. So make sure that as you're putting in all of these equations, and you'll see that we're actually looking at the design parameters of sheathing, not joists, even though our final outcome is going to be the spacing of those joists. All right, so we are going to look at bending. So when we're looking at bending for our sheathing or our deck, we're going to be using the equations up here. Make sure that it's not metric. We're looking at bending for plywood, 3 or more spans, and there's our equation. And then later, when we're looking at the plywood for shear, it's going to be that guy. And then finally, for deflection with 1/360, it's going to be that equation. All right, so going back here, I wrote all these equations over here just so we kept straight which equations we're using. And then here, we actually plug it in. So 10.95 FBKS, which comes from up here, divided by small w, which is right here, all raised to the 0.5 or to the 1/2. And that gives us a value for the max span it can handle before it fails in bending. All right, shear, we saw where that equation came from. We're going to take the FLB or FSLB over Q. We're going to divide that by W, small w. We're going to add it to 2 times D, or the thickness of our sheathing, which is 1 inch. And we come out with 89 inches. And then lastly, the deflection. Looking at that, we've got the EI times 1.69 divided by this W raised to the 1/3. We come up with 27.13. And then I just wrote an equation here to pull the minimum value from all 3 of these. And so that way you can look at just this when you go back if you change anything, and then decide on your spacing. So all these here, here, and here are just hard punched. You could probably write some kind of an equation to round or whatever based on nominal values, but for me it's just pretty easy. Just punch in, okay, 27, let's go 24, etc. So that tells us our joist spacing. So once you punch that in, it feeds this. So when we're looking at our joist design, or our stringer spacing, so basically we're looking at our joists. They're running along, if you were to look at the 90 degrees from this, they're running along and they can handle a certain span before they're going to fail in one of these 3 mechanisms. So that's going to tell us where our stringer is. So now we're looking at the joist, and we're going to use the properties of the joist to find what our stringer's maximum spacing could be. All right, so given that, we know that the spacing for these joists that we've chosen so far is 24 inches. So we're going to take W, big W, which is the total load. We're going to multiply that by the joist spacing, which is our tributary area that we're looking at here, which happens to be 2 feet, or 24 over 12. And that gives us 310. Alright, so then all we do here is we basically pull these from the same sheet, but we're not looking at plywood anymore. So for bending, we're using this guy. For shear, we're going to use this, and for deflection, it's the same. Okay, so all these equations are written out here. All of these formulas pull from, we're looking at southern pine for these items. Make sure that you're pulling from the joists, because we're looking at the joists. So you're pulling from the right data. You're plugging all these in. Same here. You'll see that it's still pulling from the joist data. And lastly, the deflection also pulling from the joist data. It's all southern pine. Alright, so then it pulls the minimum, and we're going here. I chose 108. It's slightly above, but we were real conservative here, so you know, that's a judgment call. You could even go a size smaller, and that's why it's nice to be iterative here, because if I wanted to say 96, just punch in 96, boom, everything else updates. So it's up to you. Okay, so going here for stringers, same thing. The only difference here is going back to our discussion, we're looking at the stringers right here. So we know that they're spaced 108 inches going into the page right here apart. So you're going to use that spacing, the original, and there you go. You get the load per area. Same equations. The only difference here is you want to pull from stringer data, not from the joist data. So you want to pull from here, these values, and not from here. Also, it's going to be the same wood type at this point. So you go through that, you get the minimum spacing there. Big difference here is we're going to look at the short capacity spacing, and I threw it in with these because it could govern, and in fact it does govern in this case. So when you're looking at short capacity spacing, it's going to be the capacity, which, I'll just pull up the formula, is right here, 6,000, and it's going to be divided by the weight that it's taking on. And you'll look, this is in pounds. You want to have this to go to inches, so you'll take this guy divided by 12. And you end up with, I'm sorry, times 12. So 51.6 becomes your limiting value because of short capacity, and you end up with 48 inches for your shores. Okay, so last thing, remember that you want to check crushing. So basically you've got this stringer on joist, vice versa, joist on stringer, and you want to see if this area right here is going to crush and cause failure. So you're going to look at the force over that area here. So if you were to look at the contact surface between the stringer and the joist, the stringer, remember, is 3.5 inches wide and going into the page, and the joist is 1.5 inches wide this direction. So that will show you where those guys are touching, and that's going to come in here in the area. So you're going to look at the depth of the joist and the depth of the stringer for your area, which if you look at the equation, pulls from there. So there's your contact area. Here we're looking at the amount of weight that these joists are putting on the stringer. So you're going to look at the joist force per unit area that it's taking and multiply it by the spacing. Actually, this should be PLF. So let me fix that. This is PLF, or yeah, pounds per linear foot. So this is pounds per foot. All of these are. They shouldn't be PSF. So we're looking at that times the spacing of the stringers, because that's where these are going to contact each time, and we get the amount of force that's going to be going down. So you're going to look and just take these two, take the force divided by the area gives you the stress or the pressure, which is the FC perpendicular. You're going to compare it to the FC perpendicular of Southern Pine, which is 405, and you get, in this case, that the design is is more than the capacities, which is not good. So you would want to change something in this problem. Things you could change this from Southern Pine and make it a different material. A few things here. As I was saying, you could change this from Southern Pine to another material. You could come to your chart that you have here and look at some of these FC prime values and see if any are better. California Redwood maybe, but Southern Pine's probably one of the highest here, so we might want to look at doing something different, like changing the size. So changing it from maybe a 2x10, you could change it to a 4x10 or 4x8, or you could change the spacing here. So if you decided to change the spacing, let's say you did go with 96, you can see what that does. Not quite there. Let's just try 72. Okay, there we go. So 72 inches stringers, we're okay. So there we go. We can use that. Okay, so there's what you can do, or you can change, as you go through different iterations, change, if something doesn't work out, your spacing, you want higher spacing, you can change some of these dimensions, see if a 4x8 works better, so on and so forth, and that'll get you the answers you want. So there's your solution for the spacing, and yeah, that's it for this one.